utilize the crystallography during the formation process. All right, so let's get to the first example. The motivation of this one is the design of structural materials for human body. So those metals is not just structural materials we use in airplanes and in cars, but it's also the structural materials we use in human body. So here we have the first generation, second generation of these biomaterials. It's all made by steels and titanium alloys. And one of the problems is the modulus is too high and compared to human bone. And that created a problem for the stress shielding. Then the goal for this design of the third generation of biomaterials try to match the modulus of the human bone. All right, so this created a problem, and the requirements for the implant is we want to have very high strength because that's the wear resistance. At the same time, we want to have very low modulus. So this is the requirement. We want to have 20 gigapascal modulus that match the human bone, but we want to have 1 gigapascal strength. So this is required the materials yield at 50% of their ideal strength. And the physical metallurgy tells us that's impossible. They usually yield at only 1% or even lower of the ideal strength. So in this regard, we cannot utilize the intrinsic elasticity of the material, but we have a good opportunity if we can utilize the pseudo-elasticity for ferroelastic materials. So here is the stress strain curve that I showed you because of the strain avalanche. But if we can find a way to control the deformation behavior and convert this stress strain behavior into this one, that's the goal, and we can realize low modulus superelastic metals. So that's the goal, and here's the idea. So if you look at this particular materials, so this is the titanium 2448. It's metastable beta titanium alloys. And if you look at how the martensitic transition temperature depends on niobium content, or the stress-induced martensitic transformation, the critical stress, how they depend on the niobium content, they have very strong dependence. So if you have a concentration modulation in your system, then locally you're going to have martensite that's already stable. They already start the nuclei in the system. Then when you apply a load, then the martensite start to propagate, but they are surrounded by a layer which is not ready to transform yet. So you have to increase the stress level in order to make the martensite to propagate, to transform in the next layer. But this is a kind of onion ring-like microstructure, and when you try to go to the next layer, the same story. You need to increase the stress a little bit more, then you can transform a little bit more. If you can design such a concentration modulation, you can turn this stress strain curve from this one all the way to that one. So now we got the idea, and we got the hypothesis. Say, okay, what's the fast way which allow us to test the hypothesis? So now we start with simulation. It can get us the fastest one. And so we have one is the concentration modulated system, and one is the uniform system. So when you do this stress-induced transformation, you can see you can start from the beginning, and then you can start to form martensitic embryos, and then in those regions that at the core of the onion, and then start to propagate under higher stress. So those microstructures corresponding to the different point on the stress strain curve for the first cycle, because you have to induce the formation of those initial embryos of martensite, then you have a small plateau here. When you go to the second cycle, those ones you already induced, upon unloading, they are not going to disappear. They become stable, they stay there. And then when you go to the next cycle, those ones are going to serve as the embryos already exist, then simply grow, and then they completely eliminate this plateau. So you have this stress strain curve. If you do the third cycles, you can tell these two on top of each other is quickly stabilized. If you compare to the one you have in the uniform system, you have a huge miscibility gap. All right, so that's what we have. And then, of course, if you only have the theory, the prediction, you can stay as hypothesis. We need to find the experimental evidence in this particular alloy system. We did the kappa calculation. We do find a metastable miscibility gap. And then from the atom probe data, you can also find this concentration modulation created by those kind of phase separation by spin-out decomposition. All right, so the mechanical property, stress strain curve. So for this particular alloy, you can see that go from 400K all the way to 4K. You can have linear superelastic deformation. And we strongly believe the other sister of this titanium 2448 metal-stable beta titanium alloys, that's the gum metal. And these two are very similar. So we strongly believe all those properties of those alloys is somehow it's also related to the concentration modulation, in particular oxygen in the system. So here you can adjust the system. You can have 0 thermal expansion coefficient or negative or plus. So this is the first example. The second example, if you have this concentration modulation, actually you can activate different kind of transformation mechanisms. So if you are familiar with precipitation process, this is the alpha-beta alloy, two-phase alloy. I have two different free energy curves, and they have different crystal structure. Depending on where the composition are, you can have different transformation mechanisms. And from this side, you have congruent transformation and then phase separation. On this side, you can have the classical nucleation growth. If you are close to this cross-section point, you can have the so-called pseudo-spinel mechanisms. So if you have a concentration modulation, different mechanisms, you can have different scale of microstructure you can develop. Then if you have such a concentration modulation, you can really develop a specially modulated precipitated microstructure. Then this particular microstructure is going to allow you to regulate the dislocation plasticity. The first example I showed you, that's the regulation of the martensitic transformation, which carries the plastic or elastic deformation. In this case, it is the dislocation, and you can regulate the dislocation activity by such a microstructure. So this is our hypothesis, and then we did a quick realization of the idea by doing simulations. So this is phase-phase simulation, and then we take a particular pseudo-binary alloys, and we did the calculation. We showed you can actually create such a modulated microstructure. And in the experiment, we say, okay, we can take a faster pathways to do the experiment. So we know for this particular titanium alloys, we have alpha plus beta microstructure. So if we take this microstructure, we do an upquench, then the structure of alpha is going to quickly dissolve back into beta. From HCP become BCC. Then compositionally, you need a long-range diffusion, and then they need to homogenize gradually. So by controlling the upquench temperature and time, we can create this nanoscale concentration modulation we call a ghost alpha. Then you do a quench, and you do annealing again, and you can create those hierarchical microstructures. So in this case, you can have a coarse and fine microstructures in this case. So we did the experiment, and we found, okay, you do have a mixture of fine and coarse alpha precipitate microstructures. And then if you look at the properties compared to uniform, compared to this heterogeneous hierarchical precipitate microstructure, you do see a big increase in the ductility, and also have an increase in the strength rather than sacrifice the strength. So the other way to create the concentration modulation is try to utilize the insufficient mixing during this mixing process. So to exit this one. So if you look at how this liquid mix with each other, there are two different processes. One is called mechanical mixing. So you have a droplet of ink drop into a water. This is how they try to mix mechanically. But in order to fully homogenize, to change the color from black and white into gray, you need to have what we call chemical mixing, which means that you want to mix the different molecules at atomic scale. So that's the chemical mixing. You require diffusion. Let's take a long time. In the additive manufacturing process, if you use two different types of powders, and what does the system try to mix together? So you have two different types of powders, and because the lifetime in the melt pool is so short, and they cannot mix chemically, but they can only mix mechanically. So we try to utilize this idea to design this compositionally modulated materials in this case. So the goal is try to push both the strength and ductility. If you take the traditional T6-4, it's pretty high yield strength, but the ductility is rather limited. If you take this TRIPS titanium alloys, it's very high in ductility, but the strength is limited. So we want to push both in this direction. So by using this idea, we'll be able to create very fine mixture of dual-phase microstructure. So we have this alpha prime martensite and this metastable beta in a very fine scale. So in this regard, they increase the yield strength, and at the same time, we have a lot of metastable beta, and then those metastable beta allow us to have this work hardening by this transmission-induced plasticity effect. So finally, we have this in situ deformation process. So this is us printed, and that's a different mixture of martensite and then the written metastable beta. When you strain the system, you can see how this metastable beta transform into martensite, which give you the large trip effect, which allow us to achieve this work hardening process to get pretty large uniform elongation. All right, so of course, this is a comparison of the properties of this new alloys in situ processed by additive manufacturing compared with the same alloy compared with the other method. This is compared with all the other different types of titanium alloys. So the last example I want to show you, hopefully I have enough time. And so this one we want to show you is how do we utilize crystallography to get the self-healing precipitate. So if you look at the deformation process of this nickel-based superalloy, and you form this is gamma prime, and then this is the gamma channel, you find this very fine scale, very thin precipitate. In this example, this is the eta phase. In this example, this is the chi phase. So this is a very interesting observation. This is after the material has been crept. So if you look at the details of characterization, you can find, okay, in some alloys, you have this stacking formed by dislocation. They form eta phase. This is atomic structure to show that is the ordered structure for the eta phase. But some of the alloys, you actually form a disordered layer rather than ordered phase. And in some alloys, you form this so-called chi phase. It's also ordered phase. And the others form this disordered layer. If you look at the twin boundary, you form microtwins. And at the twin boundaries, you also form these two layers of this chi phase from the ordered patterns you have there. So this is a very interesting observation. So we try to understand if you have a stacking fold or twin boundaries, they are the natural place to host those phases. But those phases, they have a bulk counterpart. They are not what we call complexions. So the question is, they are not stable. Why these appear in our alloy? So our alloy is supposed to use gamma prime two phase rather than have this eta and then chi. And the second question is, why do we care? So if we look at try to address the first question, if we look at the atomic structures of this ordered intermetallic phase, this formula, Na3X, and then beside this gamma prime and gamma double prime, that's the one we have in the traditional classical, the nickel-based superalloys. They have the FCC stacking sequence. But in the same family, the same formula, we have other phases, delta, chi, and eta. they have the HTP stacking sequence. So now this allows us to understand, it's a very simple analysis of the crystal structure. If you share this L12, which has FCC stacking sequence, by passing a Shockley partial dislocation, you create this stacking sequence, ACAC, that's HTP stacking sequence, which gives us the so-called DO19 structure, and that's the chi phase we have. If you pass another Shockley partial dislocation, you're going to have this CBC and then CAC. It's called kind of a double HTP stacking sequence. And that's the crystal structure of this DO22. That's the eta crystal structure. And then if you continue to shear, and when they develop a micro-twins at those two twin boundaries, automatically you have the structure BAB and CAC. They are naturally the chi-phase microstructure. All right, so now this allows us to understand why they form those ones, because when you try to shear the precipitate, mechanically you change the stacking sequence, and then they're going to form those phases. So when you analyze the details of experimental microstructure, you can tell this is at which stage of the shearing deformation process. So now we say, okay, let's try to utilize this observation and to design some alloys. So the second question we have, so the first part we are trying to understand that those phases are not in the equilibrium phase diagram and why they appear. So basically we say, okay, we have a very simple thermodynamic analysis. We have the HTP phase and FCC phase. In this case, FCC phase is stable in the whole entire composition range. In this case, you have two-phase mixture. However, if your alloy composition in this case, and if this alloy composition is outside the two-phase region in a single-phase region, in both those cases, if you shear your FCC phase, mechanically you drive your system into this HTP stacking sequence. This is not reversible. The system cannot relax back to FCC because the deformation is not reversible. So what's going to happen here, you're going to have the first step, you mechanically drive the system here, and then they just reach the common tangent, and then they develop this equilibrium microstructure, which give you this HTP phase. But this one is not stable phase. They cannot grow, they cannot portion. They can only stay at where you have the HTP stacking sequence. So this allows us to understand why we have this localized confined phase. So now, let's try to see how this is going to help us to design alloy. So we have, I want to draw your attention to those three alloys with three different colors, blue, green, and gold. So they have pretty close composition. So it's all in this space. What people try to do, when you design a superalloy, you want to stay in this region rather than in this region. You want to avoid the formation of delta or eta, those bulk phases, because they are detrimental. They want to stay on this side. So those three alloys chemically are pretty close. If you look at the creep performance, they are quite different. And the question is why they are so different. So if you look at the detailed microstructure, you find if you have a disordered phase form at the stacking fall, then your creep property is bad. If you have this ordered phase, if you form at the stacking fall, then you can enhance dramatically of the creep performance. So that's what we found in experiments. So now we say, okay, how are we going to utilize this idea to design new alloy? And we start with this first principle calculation, try to understand why the formation of this chi or eta phase can help us to enhance the mechanical property. And so this is the calculation of the barrier if you try to shear the particle when you form SISF or you form SESF, you want to continue to shear. Then if you don't form this chi or eta ordered phase, you stay as gamma prime. That's the barrier you need to overcome. But if you form those chi or eta phases in the alloy, then you need to overcome a much higher barrier. In some of the alloys, if you form disordered gamma rather than those ordered phases, the barrier is even lower. So this allows us to understand why if you form disordered stacking fall phase, then you're going to have much worse creep property compared to one you form ordered stacking fall phases. And the next one, we try to understand to how do we utilize this understanding to design alloys. And so previously, this is 17's work, what he tried to do to use aluminum composition against this niobium, tantalum, and titanium, and then try to say, okay, if you stay along this boundary, if you don't over this side, then you are not going to have bulk phases of delta eta or chi. But if you are closer enough to this line, you may have those localized phases. So they try to use this design criteria to do the design, but the problem is what we try to do is try to rank the alloy's quick performance in the right sequence by identify a descriptor of the alloy, which allows us to rank them monotonically. But in none of those descriptors they propose are able to do that. And then we say, okay, because we already understand this design criteria, and that's why we design a new criteria, new descriptor. So the idea is very simple. We have a two-phase mixture, gamma prime and gamma. So now, mechanically, you deform material. You take the materials to this position. If you have a system, the ordered eta phase has lower free energy compared to the disordered double HTP crystal structure. This is all HTP stacking sequence. Then the system is going to stay as ordered, and they go from here and then just down to point E. When you reach the parallel tangent, you stop. So in this case, you're going to have this eta hardening process. If you switch the order of the free energy of the ordered phase versus the disordered phase, what's going to happen, you can bring the system to the ordered phase, but the system is going to relax to the disordered phase and then reach the parallel tangent point. Point E, you're going to have disordered stacking fault phase. And then you're going to have this what we call the gamma softening. So now the new descriptor is basically calculate the free energy difference. So the larger of the difference, and then this is away from zero, that's the new descriptor, that's the best. And you definitely want to avoid that one. So we take this one. First, we try to rank this from the database. We calculate this new descriptor, and then we found they allow us to rank nicely of the performance of the existing alloy. So now we say, okay, how do we design a new alloy? As I said, if you know what you are looking for, so we boil down a very simple descriptor, and we can do very quick calculation. So we use the CAFAT method. We did just less than 1,000 calculations in this computational space. This is the cross-section along the tantalum and titanium. And this is the best existing alloy, is this one. And then we just find this one has a better, this parameter we just developed. And then we have this one. And then we present this one to NASA, and I think we were convincing enough. They went ahead, they made alloy. And so this is the result. If you take a look at this new alloy, this is purely developed by computation first. You have just as-cast polycrystalline material with fine grains compared to the best available, the NASA alloy, which is this one. So this is under this condition, temperature, stress, at this amount of strain, this one performed the best. And not just that, this is even better than the single crystal, and this is the polycrystal superalloy. It's even better than the single crystal alloy. So this is a big surprise. This is the first cycle. We plan to do many, many iterations, but this one allowed us to design a new alloy just by the first iteration. So we are pretty pleased by the result, but at the same time, we are also nervous about this result. So we see, okay, we are doing more more characterization and testing, and not just the quick performance, also the fatigue and the other properties of the system. And you can utilize this idea to design new alloys. So you can just do pre-deformation, you do aging, and you can develop this nanoscale of those ordered phases. They may have some better properties. So with that, I would like to summarize. So what I presented is if we recognize the common features shared by shear deformation, either carried by Martin-Seed transformation, dislocation, deformation twinning, or shear bending in metallic glass. They all have the same feature. That's the autocatalysis and string avalanche. If you can find any way to stop the autocatalysis, control the avalanche, you can get whatever desired stress strain behavior you want. So we have tried a few different things. The first one is by this concentration modulation at nanoscale. And we found it's very effective to control the shear deformation carried by Martin-Seligman transformation. By doing so, you can convert this big square-like hysteresis loop into linear superelastic and the ultra-low elastic modulus, which can be really good for the bio-implant applications. If you have concentration modulation, you can activate different transformation mechanisms, which give you naturally a modulated precipitated microstructure. And then if you have such a hierarchical microstructure, which allow you to regulate the dislocation activities, you can enhance strength and ductility at the same time. The last example I showed, if you can have this coupling of crystallography and deformation, and then mechanical deformation drive the crystal structure change, then you can form those localized phase. They become stronger when they order, so you can have this so-called, we call a self-healing precipitate. You can achieve really high creep strength for the nickel-based superalloys. So with that, I'll stop. Thank you very much for your attention.